Welcome, this is Dr. Plague, and this will be the last video on the Plague Mark II homemade CPU. Now it may show up again as a guest star in future videos, but until then, this is it. If you saw the last video, then you will know that the design of the Plague Mark II is complete. So in this video, I'll be making an update to the assembler so it matches the design. Then we'll create one final test for this CPU. And like the last test a couple videos ago, this will be something more practical. Something that could be useful, although it's not. Trust me, we're still just playing around here. And at the end of this video, I'll present my final thoughts on the Plague Mark II homemade CPU. So first, let's quickly finish up the assembler. I'll bump the version to 1.1. And if you watched my video on creating the assembler, then you'll know that all we need to do to add more instructions is to just add them to this here ASM structure. So I'll add in copy, which has an opcode of 5. So we'll enter 50 in hex. Then the operand is an immediate value. Next, we created the in instruction with an opcode of 3, so 30 hex. And there's no operand, so that's non-applicable. Finally, we created the jump if equal instruction with an opcode of 6, which is 60 hex, with an operand type of an address. And we can just compile this code, and that should be it for the assembler. Now, for the final test, we're going to pretend to design something. If you'll remember, in the first test, midway through the Mark II design, I made a watchdog timer. What should I make this time? Okay, I have an idea. Let's make an electronic lock. You know, like the electronics to operate the mechanism of a safe. This will be something that has a keypad to enter a passcode, and an output to send to the mechanism to unlock the lock. For the keypad, I'll just use the 4 input switches that we wired up, and I'll use the out register to create the unlock signal. Now the switches will represent the numbers 1, 2, 4, and 8, because those are the values that they each enter. And I'll just add this little overlay here to show the values. Now, with only 16 bytes of memory space for the code, we can't do anything too elaborate. So the passcode will only consist of 2 digits that we need to enter to unlock the safe. And they will be hard-coded in, so we won't be able to change them without reprogramming it. For the signal to unlock the safe, I'll use the value of 8 for no particular reason. Okay, let's draw up a quick flowchart for this program. This will be the start. We know that the user needs to enter 2 digits or numbers to unlock the safe. So the first thing I want to do is to check for the first of the 2 numbers. If the user didn't enter the correct number, then there was no match, and we'll jump back to the beginning. Else, we'll jump to the next step. At this point, the user has entered the correct first number. So, we need to wait until the user releases that number. In other words, we'll wait for a change. And if there was none, we'll keep waiting. Else, we'll move on. At this point, the user has probably released the key that was being pressed. We'll just wait until the user enters the next number. So if no key is pressed, then we'll jump back here, else move on. Now we can check for the second number. And if that was incorrect, we'll jump back to the beginning. If that number matched, then we know that the user entered both numbers correctly, so we can unlock the lock to the safe. We'll just output an 8 to unlock it. And this will be the end of the program. Now, I know what you might be thinking. We're waiting for a change to detect a key release, but what if it wasn't released and instead another key was pressed along with the first key? If we're running this at full speed, then that wouldn't matter. It'll be detected as the wrong key anyway when we get down to here. Okay, so this looks good. Now we need to translate this into assembly code for the Plague Mark II CPU. So first, let's decide what numbers the user needs to enter to unlock the safe. How about 4 followed by a 1? And all we need to do to relock the safe is to reset the CPU. Now, according to the flowchart, we need to check for the first number, and that's a 4. So I'll just copy a 4 into register A. We need to get the user input so we can check if it is equal to 4. We can use a jump if equal to do this. And I'll jump ahead to address 4 if the user entered the correct number. If the user entered the wrong number, then I'll jump back to address 1 to continue getting more user input. We can use a jump if not carry to jump back, since we know the carry bit is not set. We haven't executed an add instruction to set it. Now this step of the flowchart is complete. Let's continue. We need to wait for a change. And since register A still holds 4, and we know the user must have entered 4 to get to this address, we can just get the user input and jump if equal to address 4 if there is no change. If the jump instruction doesn't jump to address 4, then there was a change, so this step of the flowchart is complete. Now we need to wait if no key is pressed. If no key is pressed, that would be a 0. So I'll copy a 0 into register A. Then we'll check the user input against that. We'll jump back to address 7 if no key is pressed. Perfect. Now this step is complete. We need to check for the second number, which is 1. We can use the same code that we used to check for the first number, but we'll jump back to the beginning if the wrong number was entered. Okay, that completes this step. Finally, we need to output an 8 before the end. I'll just copy an 8 into register A and send that to the out register. And then for the last step, we can just halt. That's it. Notice that we used every byte of code space for this program. The Plague Mark II can only access 16 bytes of code, and we have 16 bytes of code. So don't expect this processor to do much more than this. Okay, let's send this code through the assembler. And there were no errors. Perfect. Here's the hexadecimal machine code output file. Let's enter this into the simulator to make sure this code works before trying it on the real hardware. Remember, we're looking for the key press sequence of 4 followed by a 1 to get an output value of 8. And I'm going to change the clock speed to 10 Hz, so it's not too slow, but we'll still kind of see what's going on. Okay, let's run it. You can see we're looping in this code right here, waiting for a 4 to be pressed. I enter a 2 and nothing happens. A 1 and nothing happens. Let's try 8. Nope. A 4, and we now get past that first loop and continue looping here. It's waiting for me to release it, and if I do, it gets past that and loops this section. Now it's waiting for me to press a key. I'll press 1, and the lock unlocks. We get 8 on the output. Okay, let's reset it. Let's try 1, then 4. It drops through, and if we press 1, it unlocks because it saw a 4 followed by a 1. Okay, another reset. I'll press 4, and this time I'll press a 1 before releasing the 4. Notice the execution went back to the first loop. So we do need to separate key presses with a release between them. Okay, let's unlock it. Beautiful. Let's go ahead and program this into the flash chip of the real hardware. I'll ID the flash chip, then erase it. Then I'll run the script we wrote in the assembler video and select the assembled output file and the programming passed. Okay, let's put the flash chip back and give it a test. Again, we need to enter a 4 followed by a 1 to get the unlock code of 8. And I'm running my clock circuit at full speed, which is just a little above 10 kilohertz. Here it goes. You can see from register A that it's waiting for a 4. 1, 2 does not unlock it. Neither does 2, 4. Or 8, 2. But 4, 1 unlocks it and gives us an output of 8. And we can't relock it with any keys. We need a reset. Let's try 4, 2. Nope. 4, 8. Still locked. And 4, 1 unlocks it again. Okay, let's press and hold 4 to see what's happening. And we're just looping from address 5 back to 4 while waiting for the release. Then we loop from 8 to 7, hence the blur of all the address LEDs. And if I press 1, we get the output of 8. Eight 1 doesn't unlock it. And neither does 1, 8, or 4, 2, or 4, 8. But 4, 1 does. Fantastic! Now, if you try this at home, you may need to add hardware debouncing to your switches. The switches that I'm using really don't need any debouncing, as I proved in a past video. I was trying to demonstrate switch bounce, and I couldn't get these switches to bounce. So I had to use a different switch for that. If you're interested in a simple debounce circuit, I showed one in part 1 of my videos on making a clock source. So, my final thoughts. First of all, it's quite a messy build. I mean, yeah, look at that. But somehow this mess makes me feel warm and fuzzy. So, this is not a very capable CPU. You're not going to get much functionality out of it. One big problem is that we can't access any RAM or data memory, only code memory. We also can't store data anyplace other than in a register. The I/O buses are separate buses instead of a shared data bus, although this is not necessarily a bad thing. If you think about it, we use a lot of separate input and output buses in embedded microcontrollers, but I think it's kind of unusual for this type of CPU. These are some issues that we'll take care of in the next CPU design. Another thing you might have noticed is that we had to make design changes or additions for almost all the different assembly instructions we added into it. Wouldn't it be nice to be able to add all kinds of instructions without the need to make any hardware changes? Think of a player piano, if you will. It uses perforated rolls of usually some type of paper. You can swap out these rolls for other rolls to play all kinds of music scores on the piano. The piano has a set number of keys, usually 88 of them, and that doesn't change. The piano hardware remains consistent, but yet we can replace the music rolls to play almost any piece we desire. Wouldn't it be nice to have a CPU kind of like that? One where we could have kind of like a roll to define almost any instruction we would like to execute? The opcode could decide which instruction roll to play. We'll look at doing something similar to that in the Plague Mark III homemade CPU. One other quick thing I'd like to touch on is that driving LEDs could require more current than what the 74 series logic ICs can safely deliver. Yes, I've connected the LEDs up to 74 series ICs, but even the HCT varieties can have total limits lower than what we might want. For example, the 74 HCT 541 that I am using has a maximum limit of 25 milliamps per output pin. That sounds fine, but it only has a maximum VCC current of 50 milliamps. So let's say the LEDs each drop 2 volts. Then that leaves 3 volts across each 470 ohm resistor that I'm using. That would pull about 6.38 milliamps per output pin. And if we drove all 8 output pins, then we would be pulling about 51 milliamps through VCC. A little too high. And we also need to consider the small amount of current used to power the IC itself, which is pretty much negligible. Now, even though there is a max of 50 milliamps through VCC, that refers to continuous current. So as long as we don't continuously pull that much current, then we're probably fine. One thing you might consider is to use larger current limiting resistors. I was using 470 ohm resistors, but you could use 1K ohms. That would lower the total current for all 8 outputs to about 24 milliamps, well within the 50 milliamp max. I used 470 ohms for filming purposes, since I wanted the LEDs bright enough to see on camera. But the LEDs I'm using are very old, from around the 1980s. So if you're using newer LEDs, then they may be significantly brighter with much less current. So anyway, if this were to be a heavily used CPU, then we might consider something more appropriate for driving the LEDs. There are ICs that are designed specifically to drive LEDs, or we could make our own LED drivers with some transistors. But for the Plague Mark II, I never intended to use it for any significant periods of time, so I just went the easy route. So to sum it up, I consider this CPU design to be something we could play around with. It's not something that is really useful. It's just a toy. And you could add more instructions to it. The opcode is 4 bits wide, but we really only used 3 of those, with the halt instruction occupying the entire 4th opcode bit. You could design it in such a way that the halt is dependent on all 4 bits. But really, this design is not going to give you much flexibility. In any case, if you do decide to build one, then have fun with it and make it your own. Well, that's all I have for today. Next time, we'll start looking at homemade composite video circuits. Until then, thanks for watching, and I'll see you next time, right here on Dr. Plague.